having to get started? Okay. So for this session, we're going to be talking a little bit more about shared libraries, but more specifically in terms of writing a shared library for analyzing your MPI code using the PMPI interface. So unlike what we were doing earlier, MPI actually provides us with a function that we can call instead of looking up symbol tables, and we can, for every MPI function, there's a corresponding PMPI function that takes the exact same arguments, and you can call that within your wrapper function, and then you can start creating your library. So if you want to know what the exact arguments are for the MPI functions, you can look them up on the OMPI website. They've got huge resources online, or you can just do what I did, which was go scrolling down through the mpi.h file and see what all the functions look like, because we're used to using them and then you forget what the argument types are and that type of thing. So they need to be word for word matching the declaration of the function in the mpi.h file. Okay. So why would we start analyzing MPI code as it is? So MPI is the message passing interface, as you all know, but it's a library for communicating two processes, and we've got collectives, we've got blocking point-to-point, and one-sided communication. So you want your MPI code to be doing the least amount of communication and doing more work. So the communication is just aiding the actually doing of calculations. So, but we find that the things that tend to be slowing our code down are not the large amount of calculations, it's poorly matched and poorly placed communications with lots of wait states in between. Okay, so an uneven workload can lead to waiting times on any of the processes. So you want all your communications to line up so that you don't have one process waiting for 5 seconds while another process finishes up a large computation. An example for that would be kind of the master slave. If the master is just permanently churning out a list of jobs for the slaves to be doing, it's doing a lot more work, and some of the other processes could be waiting for communication from it for a large period of time. So why would you write your own kind of profile? There's lots of tools out there already. So you might have looked at some of them, or you might have looked at none of them. But some of the ones we looked at before was Tau, Vampire, Scholastica, ISP. Those are a few of the examples. Scholastica is actually the closest to what I'm going to talk about today, because it does a lot of analyzing of wait states. So it's most interested in finding the mismatches in communications. Some of the other profilers are looking more at the amount of data you're sending. Are you repeatedly sending one send when you could have sent a large block of continuous data instead? So Scholastica specifically looks at the wait state, which I'm going to be talking about. There's lots of various metrics you can look at. There's lots of ways you can analyze your code. You can look at metrics, profiling, traces, analysis, and visualization. So metrics would be, you have to decide what you're actually interested in. Some people are interested in the time it takes for the code to run. Others are interested in how much data am I actually sending with all of my sends. Some people are worried about bandwidth and latency. Are we pulling heavily on the network while we're doing all our sends? And some people only want visualization. So things like Vampire or Scholastica will give you a nice pretty picture that can go into your report and either say that your code is terrible or put your code is really good. You ideally want it to tell you that your code is fantastic and you've got minimum amount of communications and lots of calculations. So you can do the two types I looked. So this is me kind of half describing what I did in my thesis, but also half describing why you might want to do it. So two things I looked at were sample-based and event-based profiling. So sample-based is where you look at little snapshots of the code. You don't take a record of the entire thing. You just say, I want to get an overall summary of what happened between these few lines, and you're going to ignore the rest. Whereas event-based is where your trace is triggered by the entry into a function or the exit from a function. That's maybe why we would do wrappers. That the minute your wrapper PMPI or your wrapper MPI send is called, you want to add it to a list or doubly linked list and say, all right, we entered at this time and we exited at this time. This is the amount of time I spent in my send. Okay, so traces are great because they give you so much information, but they also have the downside of you have a lot of these profilers create a trace file. So if you've got a really large computation and there's lots of events or lots of calls to MPI functions, your trace files are going to get really big, and there's one trace file per process. So it's like what Dermot was saying yesterday. If you're running this on 100 processes and they're all each outputting a trace file, that's not feasible for when you're analyzing your code. Okay, so maybe summary information is more what you're after. So possible things you can look at then are event counts, the duration that you spend in a function, and the number of bytes that you're sending, and bandwidth. So today we might look at just trying to implement maybe an event count. So counting the number of sends and receives and maybe broadcasts that are happening in your code. Okay, so a little bit more on summary information. It's collection of data in certain location over the course of the program. So you're only just looking at what is going on in one particular part of your code. You don't necessarily want to know, or you want to get a summary of everything that happened in your code. You want to get a running total of the number of sends and receives, the running total of the number of the amount of data that was sent. You don't necessarily care what happened at one individual send. Okay, so it's efficient for storage and gives a general overview of the program. A couple of statistics then you can get from your summary information would be mean, variance, standard deviation, max and min, and that type of thing. It just gives you an idea of what's going on overall. And then you've got, so this is an example of, so I created like a kind of a summary information and kind of a tracer. It was kind of a mishmash of the two, but this is just a little bit of the output that I tried to give as a summary of what was going on in my code. So I would pick a function and say, okay, there was 5 counts of that function called, and then I would get the mean, standard deviation, max and min on the time that it took, the amount of time we spent in send functions, and then I would get the same for the size of the packages that were being sent by the send functions, and then the bandwidth that was being used. So these were just 3 summary metrics that I picked. And the way I used a way you can differentiate between the send that happens on line 6 and send that happens on line 8 is you can get the return address of the function using a built-in function that I'll talk about later. But it gives you a unique ID for the function call that's happening. Okay, so I just kept the record of where the biggest and smallest sends and receives were happening and where they happened in the code. So you can use that address then to reverse engineer and find out what line that was in the code. So then when you're not using summary information, you're using breakdown information. So it stores each measurement of the trace individually. So every time you go into send, it adds it to a W-linked list. It says I entered send at X or after however many minutes since the program was started. And I was in send for this long, and I sent this many bytes, and I sent them to process 0, and it went successfully. So you can store all that type of information. You can either output it to a file, or you can add it to, say, a W-linked list with some sort of unique ID on that send. It gives more detail than the summary profile, but it does have the disadvantage of it's quite heavy on memory consumption or outputting to a file. You have to find a way of dealing with that data then. So what you can do with a trace instead is, so like I was mentioning before, that each function call has an address in memory. You could aggregate the information on what happened at just this address. So how many times, if there was a for loop on an MPI send, you could say, okay, it was called 10 times, it took this long, and it sent this data over 10 calls to that function. So you can make the trace information closer to a summary information for the purposes of finding a good way of recording it. So this might be what the trace information can look like. So say your I receive is happening on line 6, but this is the return address of that I received, but it was called 552 times. So it was in some sort of really unfortunate for loop that there was an I receive being called that many times. But you were receiving from source 1, and you received that amount of gigabytes, and it took that long in seconds. So it gives you more information about what's happening on single lines in your code. So they both have their merits, but it's if you want, you can play with them later and see which type of information you might find easier to record if you want to play with I provided a brief skeleton and you guys can do whatever you like with it. So wait states are something that, if you ask Dermot, I talked about for an entire summer, and I was seeing these wait states in my dreams because there are so many ways you can screw up MPI code and you don't even realize it. Okay, something as simple as putting a send and a receive in the wrong order can cause one of these horrible wait states. Problem is actually trying to create examples that have wait states. We all do them by accident, but when you try to create a simple example for recording these, you end up using a sleep 5 in the middle of your code just to cause a wait state. Okay, so they occur at synchronization points. So where there's blocking points in the code, you cause these wait states. So a lot of the obvious ones we would think of is people waiting at barrier for everyone else to catch up, or everyone waiting in an all-to-all communication for everyone to reach that point so that the communication can happen. But there's a lot more subtler ones that you might not have thought of while you're writing your code. So it's defined as the length of time of the interval covered by the wait state, so one process waiting for another. Okay, so even if the function call happened on process 0, the wait state potentially happened on process 1, depending on who was the guilty party in the wait state. And so the way you can record then these wait states is the address that it happened on, who was affected. So was the send affected? Was the receive affected? Who was causing it? Then so how many did you record at that point? Who caused it and who affected, and how long you were waiting? Okay. So this code, some process was process 3 was waiting for about 8 seconds because process 0 was had posted late receives. Okay, so here's a list of some of them, and I have diagrams to go with each of them so we can kind of look at how they can occur with, say, 4 processes happening. So there's some that might kind of seem like common sense. So a late send posted or a late receive posted causing another process to wait. Waiting at barriers or waiting at n/n functions, so all to all gather, all reduce, tend to cause lots of wait states. Waiting at n/1 functions, so things like reduce and gather. So the root process on gather, so gather is called on the root process before it's called on everyone else, and it's waiting for everyone to send the information to it. And then you can have a wait state on an n/1 communication, so bcast is sending information to everybody, but it posts its bcast way later than everyone else, so it causes a wait state on every other process. Early scan is, I left it out because I did understand what that was 4 years ago, and I can't remember what scan is now. So, but yeah, early scan is a type of wait state. And then we've got RMA related wait states. So who here has been doing one-sided communication and who hasn't? No? Yes? No? Are we all mute because it's afternoon and tired? So you haven't. So one-sided communication is really good because it's also kind of mind melting a little bit, but it is really cool because you can open up a window of information and you don't have to stop your code for someone else to place or take information from it. So it's if you can implement one-sided communication, it makes your code a lot faster. It can make your code a lot more interesting, and it might slow it down if you do it wrong. But it allows for, so what I've used it before is every process has a sub-block they want everybody else to be able to see, but you don't necessarily want you to have to wait for everyone else to look at your information. So you make it available for everyone to see, and they can then extract points from it if they want to, and you don't necessarily have to stop and block. You can just make it available for a large period of time.
Yeah, I mean, the main benefit of having it is that if I have data that I want other people to see, how do I know what they want to see? And then do I have to sort of have an exchange first to say, for you to say, oh, I want you to send me 6 points, and then I send you 6 points using 2 sets of outputs and video. Here it is, take what you want. But there is a coordination thing of, with this RMA stuff on, you have what are called epochs, where effectively a time where you say the data is available from now until sometime in the future. But if you open or close your epochs at the wrong time, and other people are still trying to access it, or people are still waiting to do transactions on it, then you get all these sort of situations where you end up blocking, even though RMA is meant to be sort of non-blocking in that sense of, you just say, here, go, do what you want, and then finish. But if people are still accessing it or haven't said that they finished using it at the right time, you end up with all these things of having to block, even though you don't think you really want to block.
And then the similar thing is so there's 3 different ways of blocking in one-sided communication, because you still have to define the time that the information is available. So there's GATS, which is general. Oh, I can't remember that acronym, but basically it's
something synchronization.
Yeah, it's something. Oh my god, like
There are active target synchronization.
Yeah, active target synchronization. So, and then fence is passive target synchronization, and there's also a locking system. So you can lock a piece of memory, and somebody else can access it, and then you unlock it. So it's so that you don't have multiple writes happening at the same time or multiple accesses happening at the same time. So these are all just ways of controlling who can access your data and when, but this window is open, and you use things called MPI windows. So I'm not going to focus on these too much because you haven't really seen them, but you should definitely look into them. I assume you'll get them covered at some stage, but they're really helpful if you can get your mind around them, because I spent 2 weeks trying to understand what the hell is going on, and I had some sort of eureka moment, and it made sense for about 5 minutes while I wrote this. So I have these kind of type diagrams, and we're going to go through a couple of these wait states just so we can kind of visualize how they might occur in your code. So the basic ones that you can see are late senders and late receives. So these are when we're talking about our point-to-point communication, and they can also happen with iSends, iReceives, bsends, sends, any of those types of point-to-point sends. Okay, so the late sender is process 1 is now waiting because process 0 needs to post a send, but it has been delayed. So this is causing the wait state on process 1. So even though the function was called late on process 0, the wait state is actually occurring on process 1 because process 0 hasn't been waiting at all at this time. So it's the blocking receive operation is posted earlier than the corresponding send operation. So this can also then happen when the non-blocking version of this late sender is when the iReceive, or the iReceive is then posted before the iSend, but that doesn't cause the block. It's the wait state, the MPI wait and the MPI wait all is posted before the iSend is sent. So they can't go until the send has been, I can't use my words today. So yeah, when it comes to non-blocking, the wait states in the late sender and the late receive are caused by the test and the wait calls, not the iSends and the iReceives, because they're called and they finish immediately, whereas these guys block. So they can happen with wait and test, but only in the non-blocking case. Okay, so that's the late sender. So the late receive then is the exact opposite of that, and it's what you'd expect it to be. So the late receive is the send happens on process 0, but it can't finish until the receive is posted on the other process. So there's a big, nice long gap happening on process 0. So the wait state happens on the process that is waiting the longest. Okay. So when we get to the n-by-n communications, you'll end up with multiple wait states being all being caused by one rogue process that is reached their way too early. So in barrier, we have every other process is waiting because process 1 is late. Okay, so they arrive late to the party and they've ruined it for everybody else because nobody now can move on from here until 1 moves on. And we might have set up our code that we want that to happen, but we usually want everybody to arrive within a couple of seconds of each other, or like a couple of nanoseconds of each other. We don't want to be waiting for that large periods of time for everyone to arrive at our barriers. You want to have your code written such that if you have barriers, which you shouldn't, your code should kind of just sync up properly. But you want everybody to be arriving around the same time. Okay. So the time spending in front of MPI barrier, which is the time inside the barrier. So this wait state is counted as when do we enter MPI barrier on this process, and you then need to somehow find out who is the last person to enter MPI barrier and distribute that time to everybody else so they can calculate their wait states. Okay, so this is why we're going to be talking about piggybacking messages later, which is you need to be able to send metadata with your messages so that people can start calculating their wait states. Okay, so barrier completion time is one we don't actually think about. We all expect that this barrier they should all leave this function at the same time, but that's not necessarily the case. So if process 2 leaves barrier first, but process 0 doesn't, or waits a little while, it will be waiting. this tends to be less significant weight state than we would find with the weighted barrier. Okay, but it still can cause a bit of a problem if it's more likely that your time on your different processes is not synced up correctly. They're all working on slightly different times. Okay. So it's the difference between the first person and the first person to leave and everybody else. So again, you need to be able to distribute that time. You need to be able to calculate the time of the first person to leave and distribute it to everybody else. Okay. So weight states at M by N are very similar to the barrier functions. They are, so when we've got our MPIL gathers, MPIL or all reduce are all to all. We call them and everyone has to wait for the last person to enter the function before the function can actually be carried out. So some of us might use MPIL reduce for like error checking or something like that, has everyone got a success flag up till now? If they do, we can all continue. If we don't, we should all stop. If you've got too many all reduces through your code, you could be slowing it down because somebody might have moved significantly further ahead and reached the all reduce way faster than everybody else. Okay. So that's all reduced, and then there's similar. There is a similar wait completion time at the end. If everyone is leaving the all reduce function at different times, there can be wait states at different functions. But I didn't show that picture. Okay. So we then have so things like reduce, scatter, gather, broadcast. We don't really expect there to be wait states with because we kind of assume everybody will reach it and the data will be distributed. But we forget that if one process reaches the function faster than everybody else, then there's going to be more wait states. So in the case where we have an end-to-one communication, I think that's what this one, end-to-one communication. If the rank that's the root that is waiting for all of the information reaches the function call first, it then has to wait for everybody else. So you need to, the wait time is calculated as the difference between when the root enters and the first person starts sending information to root, because then root can start doing all of its work. Okay, so if the destination process of root enters the operation earlier than the sending components, so just the first person to send information causes the wait to stop because root starts doing some work then. Okay, and then we have the inversion of that, which is the one-to-end communication, so things like broadcast and scatter. So if everybody else starts entering the function before root and root hasn't started sending the information yet, they then need to wait. So it tends to be if you've been gathering your part, or if they've been gathering if the root process is still busy gathering the information to be scattered and everyone else reaches scatter first, that you then causing wait states on the rest of the processes. You should try find a way of making them busy while the root process is gathering that information to be broadcast. Okay, so we would find that good practice might be reading in your command line arguments on root 0 and then distributing those to everybody else. But while you're reading in your command line arguments and parsing them, everybody else is doing nothing. So you might want to find something else that the other processes can do while you parse your command line arguments. Well, that's what I do because they tend to get mismatched if you don't do it that way. Okay, so this is where the ORMA communication comes in. And this ORMA communication is slightly complicated because you have, so this is in the general active target synchronization, or GATS as it's easier to call it. But in GATS you have a access epoch and the exposure epoch. So there's the people that want to access the data and the people that are making the data available to everybody else. Okay, so which one's which? The start is the start is the access. And then the exposure. I have to think about it before I say it out loud. So if we look at process 0 and 2, they are using start and complete followed by an operation, push or get. So they are the ones that want to access the information that is being made available by process 1. That's known as the exposure epoch. So it posts to say that its data has been made available, and then 0 and 2 can use push or get or accumulate as functions to access the information that has been made available by the other processes. And then, but if the post to say that the data has been made available is posted after the starts, those processes are waiting until the data has been made available. So there is, even though it's called one-sided and it's kind of thought of non-blocking, you do have to wait for the data to be made available. So if that post is, if it is posted late, you're then causing all the other processes to wait. Okay, and you can wait in start or complete depending on how your MPI has been implemented, because either start or complete is defined as blocking depending on your implementation. Okay, so it can happen on multiple processes. So there's waits happening on both of these processes because the post has been run later than everybody else. Okay, push is for putting information into the open memory, and then get is for taking it out, or accumulate is for doing action on to do action on the data, but that's in the memory. So then weighted fence is the passive synchronization. So if the fence is posted, if there's a mismatch in the time the fences are posted, then process 1 is waiting way longer for the second fence to be posted on process 0. So you cause a weighted fence. Okay, these are just some of the different types of wait states. There are a few more, but I haven't put them all in here yet today. Okay, I think they're really cool. I spent a lot of time trying to think of quirky ways of calculating these, and a lot of it involves sending piggyback messages. So with your buffer of information, you're going to send the time that you started your call so that the receiving process knows when you started. Or you might need to send an extra communication to say, I just finished, and send it to the person that you did the communication with so that they have the time. So you need to find a way of making all of these times available to everyone else for calculating these waiting states. So yeah, I kind of melted my brain over these for a whole summer. So I'm quite, I think they're quite cool. But so Scholastica is one of the profilers, and it's a trace-based profiler. So you run it once to generate the trace of the program, and then you run Scholastica on the trace for it to analyze the wait states. So it outputs all of the start and stop times and functions to a file, so that you can then post-run can do the calculation on how many of these were wait states. So when I was implementing this, I was trying to do, I did it, but I didn't know how well it worked, but I did it. But it was a real-time calculation of wait states. So while the program was running, it was also trying to calculate it wasn't waiting for long periods of time at the same time. So it was a library that was loaded over normal MPI executables. But if you are looking for profilers to play around with Scholastica, it's quite cool because it gives you nice visualizations of where your wait states are happening, and it is very unforgiving. It gives you down to the nearest microsecond of how bad your code is. So it's really good. Okay, so I've talked a lot about it, but not actually put it on the screen at all. So PMPI is the built-in profiling interface into MPI. And what it is you can create wrappers for MPI functions. So it allows you to call MPI functions within an instance of a new MPI function. So you can create a library and preload it and use that instead of the usual MPI. So people use it mostly for debugging and profiling. You wouldn't be using PMPI in your runtime code. So it allows us to maintain the behavior of the original function. So there's no, the send happens the exact same way. It takes slightly less time than if it had been run normally, but the things that it executes are the exact same. So you don't lose any of the functionality of the function. Stupid sentence, but you don't lose what the function does by calling the PMPI instead of MPI. So that was the link to the MPI.h on Shook. I think it's worth looking, and I might open it up later on and just have a look at MPI.h, because it gives you the big long list of how each of the functions is declared and all the arguments that they take, so that when you want to create your own wrapper functions, you have the exact arguments that you need for declaring them. Okay, and then so it just gives a list of the definitions. So the first time you look at it, you get a bit mind-boggling, because in that file, the MPI functions are declared, but the PMPI functions are also declared at the bottom of the file. So they're both declared in the same header file. And all of the all of the variables are also declared. So like your MPI struct, your MPI status, all of those values are defined because they're just wrappers for integers and things like that. So they're all defined in that folder as well. So it is worth actually having a look if you like using the MPI just to see. It also gives you a list of all the functions you might have never thought you needed. And it gives you a list of functions, but it also gives you a list of functions that are not used anymore or that have a newer version of that function in the library. So you might end up using the wrong one. So, but it's a fun file to look at. We'll look at it a little bit later. So this is a very basic example of a wrapper that I wrote for MPI send. So you take your, actually that's wrong because it should be const void star buff, because I know it's because I've looked at it way too many times. But so the definition actually in this one is wrong, but I'll fix it. But so you take the exact definition that was given for the sentence from MPI.h. So you just go in and steal the exact line, or it's on the OpenMPI man pages for these functions. And then a very simple function is just calling the PMPI version of MPI send with the exact same arguments that were passed into the function. And that could be it. That's your wrapper. That's a wrapper done. And then you return the value of PMPI because we know that all the MPI functions should return an integer. So you could actually put some error checking into MPI send and you check for MPI success and that type of thing if you wanted to, or you could do it in your own code. So what this code is doing is it's using time spec, which calculates time to nanoseconds, which might seem like overkill, but when you're testing silly functions that just send one integer, they happen so fast they come up as 0 in microseconds. So at one stage I had to change it to nanoseconds. But because I was getting negative numbers in time, and that was really annoying. So what this is doing is it's getting the start time, so the time before we entered the PMPI send, and the time we recorded after we left the PMPI send, and then we calculate the difference between those to get the time in nanoseconds using some function I've made up somewhere else, calculate the difference, but it's just -9 time-wise. And then you can calculate the size. So the function gives us the size of the data that you're sending. It's just count by size up top. So that's the amount of bytes that you're sending. You then can calculate bandwidth, and this is the function built-in return address 0 that gives you, it looks up the trace or the backtrace of the executable, and it says, okay, well, this is the address of my function when I was called. So it's the address of where MPI send was called. So when I was creating the library, this was what I used as my unique ID for the function call. So for when I was creating the W-link lists. And then here, you can just add whatever you want to do with that data. You might just want to print it out. You might want to add it to a list. You might want to just increment some counter that is counting the number of sends we used. But you can do whatever you like with these, and that's you almost have to think what you would possibly do with it, because the scope of what you can do when you make these wrappers is so big. Because you could just make a wrapper for the sake of it, or you probably have a plan to do for something to do with it. So I wanted to record all of this data, and so that I can have it at the end and get the summary information on all the sends, and also get a kind of partial trace on all of the code. And it was spewed out to files at the end, or it was spewed out to the terminal, depending on what my flags were. So, but the main thing is, PMPI send takes the exact same arguments as MPI send. So you don't have to change them, but you can, and I will. But you don't have to change the arguments. And if you want your send to happen as it would have normally, you just leave the exact same arguments. Okay. So the one weird thing that there is I still I've forgotten this up until about 2 days ago, is a call to PMPI takes less time than a call to MPI. So even though we're adding all this extra functionality to the code, you creating these wrappers is not significantly slowing down your code. Because I remember on the last couple of days before my thesis was due, and I was like, oh, I don't want to run this. It's going to tell me that it's making it really, really slow. And it was nearly faster. And I was like, how is this working? So it's because the symbols are all, so the symbols with PMPI have already been
Resolved.
Thank you. Resolved, yes. It's a word I can never remember when I try to explain this. So the symbols with PMPI have already been resolved, so it doesn't need to look up the symbol table to look up what version of MPI send we're using. It just calls the PMPI symbol. There's only one. and it's already been resolved. So it's faster to call it. It does the exact same thing. The function it completes the send as it would normally, but it's just slightly faster because it doesn't have all of the symbol table lookups, so it's already done. There is a really cool paper on PMPI that I've linked at the end of this that you can read, which I have at some stage in life. But no, it's so it is faster. And I ran an experiment at one stage that was like send, an MPI send 10,000 times of of a really large array, and every time it was coming in faster to do the PMPI send than the MPI send, which was really weird. So that's PMPI. So I now want to say just a little bit on piggyback messaging. I'm going to use this picture to describe it for the moment. There's 3 types of piggyback messaging that we can do, and there's also another paper linked to the back of this if you're interested in this sort of thing. Because I thought this was a brilliant paper when I read it. So there's 3 different types. There's explicit packing, which is using the MPI pack and MPI unpack functions that are available in the library. There is using data types and absolute addresses to send to, instead of packing the data, just send the data with the correct addresses packed into a new data type. And then the last one is sending separate messages. So I thought sending separate messages was the least efficient way because you tended to interrupt and get in the way of the normal messages that were being sent with the MPI send. So if you send another message after that, you're kind of causing wild chaos. But what you can do is create what's called a piggyback communicator. So a separate communicator where the messages on that communicator are only to do with your profiling layer and nothing to do with the original messages that are being sent. So it means that you don't get any mismatches of sends, receives, I receives, all that type of thing with the message that should have been sent in the first place. So I didn't do as much of that as I did of the absolute addresses. So what's happening in the first one is we use MPI pack. So we have our piggyback data and our message, and we have a buffer that we have declared to be the size of one double and whatever the data type was that you were sending in the first place. So I'm saying one double because say it's the send time of, or the starting time of the function. And you want to send that to the next process. So what you do is you MPI pack the piggyback data in, and then it moves the pointer along, and you can MPI pack the message in, and it goes into the memory directly after that. And then what you can use is a constant called MPI bottom, which is a pointer to the start of the memory of this data type that you're sending, and it will send the 2 of them to the next process. But the only thing is, if you've changed the send on this process, you need to change the receive on this process, because on this process we're sending a double and the message, but on this process it used to think that you were only receiving the message. So you now need to change your receive so that you're receiving the time and the message, not just the message itself. So if you change one sending function, you need to change the corresponding receive function. But that also can cause problems if you've got a send that's going to an iReceive or an iSend that's going to receive. So if you've changed one, you need to change all of the point-to-point communication so that they're all ready to accept this type of buffer. Okay? And so the second type is where we declare, I actually have code to go with that packing one. Hang on. Okay. So this is the packing example. So at the beginning, you're declaring a buffer of size char that's big enough to take a double plus the size of the data type that was being passed to MPI send or whatever this is in the first place. Receive or something. So in your MPI send function, you pack the timing variable of one double into the new buffer at the position. So position is set to 0, and then position is incremented by 1 after you've placed one object in there. And you then pack the buffer in beside the time into the new buffer at the position, which has been increased by the size of a double. And then you can say int val MPI send new buffer. Oh yeah, no, this isn't MPI val, this is MPI packed. Okay. So you send the new buffer of a size with this new data type called MPI packed, which is built into MPI, and you send it to the same destination and tag. But you can only do this if you have changed the receive side of things. So on the receive side, you should be receiving a new buffer of the same size with MPI packed, and then you unpack on the receive side. So you extract the buffer, or you extract the time variable as a one double, and you extract the original buffer as by count and time. Okay. The only thing with this is you're copying memory, so you end up with double the memory, as in it's copying the memory into a new buffer. So this is why this method is less effective than some of the others, because you are now ending up with a copy of the buffer that you used in the beginning. So you that's not ideal. You don't want that at all. So what we're going to look at instead is taking advantage of absolute addresses. So objects in memory have an absolute address in memory when they've been dynamically allocated. So what you can tell the send to do instead is take, this is the address of my piggyback data and the address of my message, and I want you to send the two of those combined and with their addresses, but you don't copy it in. You're just declaring a new data type where those are already stored with those addresses and sending them over, and they're received on that side. And I will see if I have code that explains that better. Kind of do. Okay. So what we do is we say we want to create a new data type. So we want the new data type to be of one double followed by size by the type. So we're going to say that, so when we're creating new data types, we need to define the types that are in the new data type, as well as the displacement and the count of each type. So we get the address of the time variable, and we get the address of the buffer that's being sent. And we say that the first type is double and the second type is the data type that was passed into the function. We then create a new struct of 2 with one double and count by size of data type with those displacements that we've calculated already. And we commit this new type, and we can then say that we want to so this is an example of broadcast. MPI bottom then is a pointer to the start of the data in this object, and we only want to send one of those objects, one of the new data types, to the root. So this way we're not creating a copy of the data. We're sending the addresses of the data so that it can be accessed. Does that make any sense? Probably not. Does that make any sense, or will I try to say it again? You're not sending the physical data. If we've got the addresses, we can send the reference to the memory instead of the memory itself.
No, you're still sending the data.
Yeah, but you're not making a copy of it. Yeah. So you're making sure that the new data type is storing the memory, but it's not creating another copy of it. It's just a new data type. Yeah. And it also, if you do it this way, the instance of the object has to survive the send and the receive. So what I created was one of these globally doubly linked lists so that the time existed beyond this, so the time value and had to exist beyond the scope of the MPI sent, or it wouldn't have sent. So it has to exist beyond the scope of the function.
I think that we would have to copy the data at some point, regardless of what we do. Because to send the data, we need to copy into a buffer which we can send from. So I guess the difference would be that this is automatically, so you can overlap with some computation, and this is potentially something that data types provide for you. But
no, I mean,
it was
yes, and you're right in that if you're doing a send, at some point the data gets copied from where you have it in your user space into a buffer that then MPI takes away. If you do it the other way, you're copying from one user space place to another user space place before it gets copied to yet another buffer.
okay.
Where with this way, you have the user space, you define a new data type that has a bit here and a bit here and a bit here that sort of skips through the address space. And then when you go send or broadcast or whatever it is that you're doing, the data that gets pulled into the library level buffer is just the bits from the places that you've put in through this new data type. So you don't end up with two copies of the data in user space. You only end up with one copy. The original is only the one that's in user land, And then in the MPI library, yeah, under the hood, yeah, you still end up doing the copying, but it's one less copy of data. And especially if you've got a large data type, that takes a lot of things off. Because also if you've got a very large data type, the library doesn't take the full copy of the buffer. It just takes the first bit, sends it, takes the next bit, the same buffer, sends it, takes another bit, sends it. So where if you're doing it the other way, if you have a large data type, you have to have a full copy of the data plus your extra one double at the start or whatever which from the piggyback message. So it does save a lot of memory if you go this route rather than the other route. Yeah.
But because we're using addresses, that's when they have to live beyond the scope of the MPI send, because if they're removed before then the data is nonsense when it's sent. So you have to have kind of global. So this is why I was using doubly linked lists. So when the send happens, I would update the doubly linked list, and the time in that doubly linked list was then sent, so that the object lived beyond the scope of the send. So that's packing and unpacking, and then the absolute addresses, and then the last one is so for every message N that's sent, there's a piggyback message NP that's sent behind that, and you might be sending 2 or 3 doubles or something like that directly after or before you've sent the PMPI call to say MPI send or something like that, and it'll send the metadata that you want, but you need to do it in such a way that it doesn't interfere with the original send. Okay, so it needs its own set of request objects or status objects, or maybe its own communicator, just to make sure that it doesn't interfere with the other sendings that are going on. Okay, so that is kind of it on kind of wait states and PMPI. What we're going to do later is we're going to look at another example of using DL symbol to look up the MPI sends, and then a nice example of why we would use PMPI instead, because it's a lot less involved in it and it's a lot less overhead with it. But we can do that in the lab in kind of 15 minutes if you guys want to take a break now for a while. We're good? Anyone have any questions? I know I just talked a lot about wait states and probably nobody cares about them, but I really do. So. And we'll look at just how we might add files to the library and that type of thing, so that you can add your own. Say, well, I think I have an example where we might try and implement bcast or something like that, so it works as well. And we can add some counters or something to it if you want. Or not, because it's Friday and everybody's super chill. So any questions?
So these 3 ways of implementing I don't know if you have a conclusion on which is the best one.
I found the middle one to be the best one because I had most control over it, because this one was causing me to have double memory every time, as in I was always using more memory than I needed to, because the second one was easier because I was using less memory, but it also was more complicated because you needed to make sure that the addresses existed after the send happened, as well as when the receive was happening. So you needed them to live beyond the scope of the function. So you needed to create these global entities so that, because the sends weren't working, if you created a local variable called double time, sent it, and then the function finished, and then the corresponding receive would receive gibberish because the variable was only local to the function. So you needed to implement this entire global record space where you were recording the times for all these things so that they could be received by another process. So this was easier, that was better. And then the last one I just didn't like because of the other communicator layer that was going on, and it was getting a bit messy. But I would have liked to look more at the other communicator as well, if I was to go back and play with this again, because I thought there was a lot of scope there for kind of just to get around the idea of interfering with messages and that type of thing. Because when I was first playing with it, a lot of the messages were kind of just interfering with other messages because I was doing silly things. But no, the middle one ended up being the best one. And when I actually emailed the guys that wrote the paper about it, because I was trying to figure out which one was the best one, because they were kind of drawing conclusions on all of them with advantages and disadvantages. And I was like, well, if you were going to try this, which one would you do? And they said the middle one, because I actually have the copy of the email somewhere. But they said it was just easier for you're using less memory, and especially when you're doing so many sends, and you could be running this on quite a big system. If you're doubling your memory each time to pack and unpack, it just becomes annoying. Yeah, it ends up being the middle one anyway. But it's fun to think about them all because they would all kind of work in different scenarios. So if you're doing simple sends and receives, the sending another message actually isn't that messy. But if you're doing a send and an I receive and a wait, then it gets more messy.
Because you said that the answer, the second one is the best. Is it more appropriate to say it's the best for monkeys or in general? Because
I think
I can think of a case where the message itself consists of gathering data from various parts area of your memory, and then maybe I want to have control of that. Maybe I can parallelize this thing and I can pack it up much faster than the API computation can do that.
I think you'd have to try it is the thing. You'd have to play around with them and see which one suits you best. Because I did try this one and I didn't like it, so I went on to the next one because the first one wasn't working for me. So I think this is why they just go saw 3 in the paper, is because it would be kind of implementation dependent on which one is better.
I think there is also one more example where the B case would not work very well is if you have a very large linked list, the amount of effort for describing that linked list would be about the same as packing it and sending it.
Yeah.
And you would be a lot better to just do the packing and sending, the overlapping yourself. So probably that happens when you use data types, that happens behind the scenes, so you don't have to do it yourself. But in this case, it's better to just do it yourself.
Fantastic. I mean, if you're using, but even if you're not doing any of this big enough stuff, I mean, if you're using a dynamic structure like linked lists or binary trees or whatever, MPI is not the most friendly because it assumes that everything is an array, right? So it's designed for contiguous memory access. You can do a bit of messing with getting that to work if you do tricks like pre-allocating all of the potential elements in your tree ever as a single block and then having pointers backwards and forwards between them. And then you can do the thing, say, of like in B, of making a virtual data type that just pulls out the non-contiguous one that you want to send or something. But yeah, I mean, if you're using something that isn't an array, then yeah, you're nearly back to packing no matter what you do. And in that case, packing in one more double isn't a, But yeah, if you're doing scientific computing, it should all just be big arrays and matrix anyway, right?
Yeah, pretty much.
Yeah. If I have 1 million particles in my box, I have an array of x equals 1 million for their x position, and then y for 1 million. And, yeah. Don't be building trees. Don't be a computer scientist, right?
Well, there could be trees in this case.
Well, okay, that's a bad example. But yes.
Parents will know.
Yeah.
But will this approach work if, for instance, we're trying to send some data between programs that are written in different languages, or for instance, from C++ code to Fortran?
As long as you're consistent
Yeah.
in doing things on both sides.
I don't know.
But are you writing? I suppose yeah. If you have a C program, it's a C++ program that is then sending data to a library called, it might be in Fortran or something underneath.
No, it's just that two independent apps. One could be written in any language, one is definitely written in Fortran.
Okay, but then you're not talking MPI.
Well, still I'm using APIs.
Well, there is MPI in Fortran.
No, but like if you've written one executable, or are you using the MPI to dynamic process?
I'm using dynamic processing.
Okay. Yeah, I think as long as you're consistent on both sides, it should probably work.
Okay.
You'll have to modify your send in your Fortran version and your send in your. But if you've written a Fortran program and it calls MPI send, if you preload your library with the new version of MPI send like we were doing this morning, then yeah, you should still only have to write one piece of code to implement the PMPI layer. And you should be able to call that from both C and from
The
Fortran.
problem is there's an extra argument in every Fortran call, so I don't know how does that work. As in, there's an I error instead of.
Yeah, but
So-
can you not put it, like, can you make your things with the bar arc, or you just have to do two implementations?
I didn't try, as in, instead of using Fortran, I was using.
It should, there's no reason why it shouldn't work. Okay. But you're in a very odd place, right? Not many people use the dynamic process stuff. But it is cool. I'd be interested to see what you're using it for. Yeah, it's explains. Yeah. Okay.
Did anyone else have any questions? No? Okay, we'll take a break and head to the lab then.
Before you break, why don't you give Dylan and Louise the applause, thanks. And of course, we head to the lab. Just a timetable for Monday. I put it on the web page in case you used it. Make sure you had information. So the good news or bad news is you're starting early on Monday because we've got a busy day. So we're starting at 9 o'clock. I'm afraid you've got a long day learning about Xeon file transitions.
Where are they doing that?
Oh, what interesting. And as well, I hope you're also in a little mini project as well. I hope that's making some progress. Perhaps you can send me an email over the weekend with your final groupings and choices and so on. I'll send you a reminder, but just so I can organise a timetable for Thursday for presentations. And I think we should be able to get it done in maybe an afternoon session or something, and then I'll give you a day off on Friday. Okay, good. So if you remember, please just send me an email. I'll send you one to remind you, but send me an email with perhaps the group that you're working on, the topic, and then we'll organise a timetable around that. So, okay, good. All right, so you're in the lab at 12:30, right? Yes. Oh, good.
Well, you know, it makes me more muscular. Well, okay, so they're the conversation would be kind of